the initial web cache poisoning with an unkeyed header. In this level, they want you to poison the main landing page. And the main landing page is going to handle some input from the user that gets inserted into the content on the way back on a subsequent request. And that content being inserted is not keyed, meaning that a subsequent access can actually get the poisoned content instead. And the goal of this lab is to execute an alert of document cookie. So to change the content in a way that it points to code that will execute this document cookie. So we'll bring up the lab. This is the lab, and the vulnerabilities on the main page. So if you inspect this page, and what we're going to do, the first thing I want to do is show you how the web caching works, the mechanism. And so what I'll do is I'll reload this page, and you'll see that the initial request to the main page is sent, and then all of the embedded content is returned. And if you go up to the original request and you see the headers associated with the original request, you see that in the response headers, you have an age of 0, meaning that this is a brand new copy. You also see this cache control header, which says the maximum age of a cached copy is 30 seconds. And then you see for this particular request, since I haven't hit this page in 30 seconds, is that ends up being a miss. And so these three things are the things that control whether or not you get a fresh copy from the origin versus whether or not you're served a previous copy. Okay, so now if I hit reload again, I might get another miss because I've been talking for more than 30 seconds. And so you'll see I get the page again. I'll click on this thing. And of course, it says age is 0, and it's still a cache miss. But if I hit reload very quickly, you'll see that the next request will get the cached version of this. So I'm going to go up to the top. And then here you can see the version that I get is 16 seconds old, and it's a cache hit. Now, the question with this lab is whether or not you can poison any of the content on this main page to get it to point to content that you control. And so if you take a look at the elements of this page, one of the things that you'll see, and this is part of the code lab that I want you to find, is that you can see there's a script tag that points to a tracking JavaScript file. And you can see rather than having the source be a relative path like /resources/js/tracking.js, you see that the actual host name has been included in this URI. And so you see the / saying this is a host name. They omit the HTTPS : / or HTTPS : because it's just assumed. And so this is the reason why in the lecture I talked about X forwarded host. Maybe it's pulling this host name from that X forwarded host header. And if that X forwarded host header is not keyed in the cache, then this you could poison and then have a different client come in and get the poisoned result. So that's what sort of the intent of this lab is to see if we can inject a rogue host into this URI. So this is a program that attempts to do so. What I'm going to do is I'm going to copy the URL of this the level site, and I'm going to use it in my program. And then you can see for this the first part of this script, it gets the site URL, and then it tries to inject as the X forwarded host my odinid.net. So I'm going to try and redirect the tracking script to go to my site instead of the legitimate page and see if this actually works. This is a vulnerability in the level that pulls the host name from this header, and the adversary can control this header. Typically, this header is added by the CDN proxy or the web application proxy. But if the adversary sets this and is allowed all the way through, then you can see that the adversary now controls this header. So what I'm going to do is I'm going to get this the original page using this header. I'm going to see whether or not the thing hit or missed. And then I'm going to find the embedded script tag that we saw earlier on that page that we saw here. And then what I'm going to do, if this is a miss, that means that this has been poisoned. The content that I get back has been poisoned. And then what I'm going to do is, as a regular user, so you see in the first request, I am, as an adversary, injecting this header. The second request, this is just from a regular user. So I'm just using the non-session based get from the request package. I'm just going to get the URL without the headers. And I'm going to see whether or not I'm going to get the actual poison script URL as a result. So I'm going to run this thing and see whether or not that request will get poisoned. So it's going to install this stuff, and then the first request happens, and it's going to see if it's poisoned, and you say this has been poisoned. So there's a miss, and you can see on the return, the script source now points to a bogus domain. And as a follow-up, so this is done as the adversary has managed to poison this link, but then the subsequent access by the victim, the legitimate user, sees this poisoned link on the response. And this is the vulnerability, because this can now be pointed to a domain that the adversary controls. Okay, so now we want to point this to some area that we control. And so for for this particular level, we have access to the exploit server, and this is a place where we can actually host arbitrary content, a link, a domain where we can host arbitrary content. And so in this case, I can specify the file path I want to store a particular body content. And then this will allow me an interface to store that content at a particular URI. And you can reverse engineer that form in terms of how you submit content of your own. But I've written a program here for doing so. So this is the next part of this script. What I want to do, the goal is to point the content of that embedded link, the tracking.js. I want to hijack it so that the exploit server hosts it. And at this URI, because this is what the web application is pointing the user to, on the exploit server, I want this URI path to have stored in it the alert document.cookie. And so that's what is stored here on this URI from the exploit server. And this is a program that does that. So I'm going to run this thing and then allow it to store the content in the exploit server. I'm going to pull the exploit server URI straight from the original page. So that's what this is doing. It's going to parse out the exploit link from the exploit server and then get the host name from it. And then from there, I'm going to use that. I'm going to post the exploit there. So you see this ran. I didn't print anything out here, but if I go back to the exploit server and I reload this, you'll see that it's been stored. I could have manually done this, but I figured we're doing this in a CS class, so I just programmatically did it. And so you can see at this route, now you have this alert document.cookie. So now we can finalize our exploit on this thing. And that's the next part of the lab. So we have stored our payload. The next thing we want to do is poison the landing page so that the embedded tracking script will point to the payload that we just uploaded on the exploit server. And to do that, this is the program that does so. I'm going to uncomment it out and then walk through what this does. This again gets the exploit site from the exploit link because we actually want to poison the tracking URI to point to the exploit server's version of the tracking script. And then what we're going to do is we're going to use that poisoning header, the X-forwarded host header, to point the route or the URL to the script source to be the exploit site / resources / js / tracking.js. And then what we're going to do is we're going to, in a while loop, we're going to try and poison the original site with this header. And then if it is a miss, that means we were successful, right? Like we were able to inject a new copy with the poisoned exploit site as the embedded link, and then we're done. We have redirected the client on a subsequent, the victim to it on a subsequent access to the exploit server, and then the alert will occur. If this is a hit, that means we have to wait. And so we have to wait. We're going to parse the maximum age of the cache content, which is 30, and then we're going to wait a certain amount of time until so 30 minus whatever the age of the current content is. We're waiting for it to expire, and then we're going to sleep that amount and then try it again. So that's what we're going to do in a loop until we've successfully managed to poison that page. So I'm going to run this. And you see it's going to wait 26 seconds. So the first thing failed, it hit, and it needs to wait 26 seconds to expire the cache. So we're going to wait 26 seconds. And then after 26 seconds, we're going to poison the cache with the exploit site. And then a victim is periodically going to access the page. And as they access that page, they're going to access that tracking script, the poison tracking script, and then that's going to create an alert. And so here you can see that this thing missed. We poisoned the cache, and then it detects that we have solved the lab. And so one of the things you can do to see that it did get poisoned is to inspect this and to reload the page. And then what you can see is when reloading this page as a regular user, I see this alert pop up. And then what you can see as part of the actual URI, you can see that the exploit site is now, it's pointing to the exploit site on, instead of the legitimate site. And so that allows you to get the alert and solve the level.